Welcome back to Physics 2. I have just a few reminders before we get started with today's material, just to make sure that we're all on the same page. So the first reminder is that there are 2 homework sets that are going to be due next week. The first of these is an Introduction to Mastering Physics homework, and that's going to be due on Tuesday next week. So today is August 26th. This is Lecture 2. This Introduction to Mastering Physics homework, which is the homework set that doesn't require any physics knowledge to complete. It's just an introduction to that Mastering Physics platform. That's going to be due on Tuesday next week by midnight. And then the second homework set that's due next week is the Chapter 22 homework, and that will be due on Thursday next week. And then some other reminders are next week you need to pick up your lab kit on campus unless you've arranged with me to have it mailed to you if you're out of town. And so you'll want to stop by campus on Tuesday or Wednesday, and the time windows to stop by are given here. And you won't pick these up from the bookstore. You'll be picking this up from our lab assistant, who will be waiting outside the northwest corner of campus by the Partnership Center. And there's a map to find her on our course website under the labs folder. So you want to make sure that you make one of those 2 time frames. That's when she'll be there handing out the kits. And to pick up the kit, it doesn't cost anything. It might be good to bring an ID, and then you should also bring a mask, just as you drive up to pick it up and you unroll your window. It'll be nice for Jamie if you're wearing your mask. And you don't need to get out of your car. You can just drive up to the location where she'll be. Okay, so let's see. Other things just to remind you of. Your first lecture quiz associated with Tuesday's lecture is going to be due by tomorrow night. That's the Lecture 1 quiz. And then there'll be another lecture quiz associated with today's lecture, and that's going to be due on Sunday night. So we'll have this schedule that you'll get used to, where for every Tuesday lecture there's a Friday lecture quiz, and for every Thursday lecture there's a Sunday lecture quiz. So the lecture quiz always follows 3 days behind the lecture. And if you have any questions about upcoming due dates, I'll have my office hours today, Thursday, from 1 to 2 and 5:30 to 6:30, and then on Tuesday and Thursday again next week. So those will be my regular office hours this semester. What we're going to do again today is finish Chapter 22. And Chapter 22 introduces us to electric charge and electric force. And last time in lecture, I introduced the idea of defining the basic properties of electric charge, and then also we discussed developing an atomic level understanding of the charge model and using it to explain basic electric phenomena. And at this point of the course, you should be able to explain why it is that this comb is able to pick up these paper bits of paper. And if that isn't something that you understand after the first lecture, you can go back and review the first lecture, or we can discuss it in office hours if you like. And so far it's been a qualitative introduction to ideas such as the one shown in the photo. But what we're going to do now is turn towards a quantitative discussion with the introduction of our first quantitative equation, which is called Coulomb's law. And we'll use this to quantitatively describe the force between 2 charges. And then we're also at the end of this chapter going to do a brief introduction of the electric field. And then the electric field that we briefly introduce in this chapter will be much more fully discussed in Chapter 23. Okay, so let's get started. So what we learned last time is qualitatively, like charges will repel And so if we have two positive charges, they're each exerting a force on the other, which is acting to push each other apart. And so that's a force of repulsion. And on the other hand, unlike charges attract. So if we have a positive charge and then a negative charge, they're going to exert a force of attraction on each other, and those forces then will be acting towards each other. And what we want to do now is do more than be qualitative. So we want to be able to do more than saying like charges repel or unlike charges attract. We want to be able to quantitatively calculate the amount of force that's exerted by this electrical force of attraction or repulsion. And the fundamental equation that we're going to make use of to do this calculation is called Coulomb's law. Coulomb's law is named after Charles Coulomb, who was a French physicist living in the 1700s. And he did some experiments to discover that the force between two charged particles depends on both the charge on those particles and also the distance between them. And the equation that was arrived at is the equation that's shown in this red box. So what this equation says is that we can calculate the magnitude of the force that's exerted by one charged particle on another by multiplying 1 over 4 pi epsilon naught, and this is just a constant that has a known value, and the epsilon naught in this equation is equal to 8.85 times 10 to the negative 12, and the units for that are Coulomb squared per Newton meter squared, and this constant is called the permittivity constant, and it uses the Greek symbol epsilon naught to describe it. So this first part of the equation is just a constant. And then the other values in this equation are Q1 and Q2, where Q1 and Q2 represent the charges in coulombs on each of the two charges. So in the example that's shown here, the positive charge on the left has a charge of Q1, positive charge on the right has a charge of Q2, and in SI units we would measure those charges in coulombs. And then R in this equation is the separation distance between the two charges. And so that's shown in this lower picture. We would measure R from the center of one particle to the center of the other particle, and its units would be in meters. So if we work out the units on both sides of the equation, they should be consistent. On the left, we've got force, which would be measured in newtons, same unit that we used in Physics 1. And then on the right, we would have 1 over the unit of epsilon naught, which is a Coulomb squared per Newton meter squared. And then we have the two units of charge, which is a Coulomb times a Coulomb. And then the distance is measured in meters. So we've got a meter squared in the denominator. And we see that the units are consistent on both sides of the equation. The coulombs cancel from top to bottom. The meter squared cancel as well. And all that we're left with is a Newton, which is the unit of force in the SI system. So this equation will allow us to plug in the two charge values, plug in the separation distance of the two charges, and then calculate the strength of the force that's being exerted between the two. This equation will allow us to calculate the magnitude of the force, and then we'll recognize the direction by whether the charges are like charges or opposite charges. There is a shorthand that we can use when writing Coulomb's law, and this is something that I'll adopt quite frequently. What the shorthand is that instead of writing 1 over 4 pi epsilon naught in Coulomb's law, we can adopt a new symbol, which is the lowercase k as defined here, where k is defined to be equal to 1 over 4 pi epsilon naught. And then if you plug in epsilon naught as 8.85 times 10 to the negative 12 into this equation, multiply it by 4 pi, take the reciprocal, what you'll end up with is 8.99 times 10 to the 9. So this is an alternative constant that we can use. It's called the electrostatic constant, and it is a constant that, along with the permittivity constant epsilon naught, will be given to you on an equation sheet summarizing important constants and equations that you can use on the exam, so you don't need to memorize it. And then Coulomb's law written with electrostatic constant becomes a little simpler. F is just equal to K times Q1 times Q2 divided by the distance squared. And we'll see how we can use that in an example. So in this example, which is number 14 from the end of chapter 22, the problem describes two small plastic spheres that each have a mass of 2 grams and a charge of negative 50 nanocoulombs. So they have identical masses and identical charges. And the symbol that I'll use for their charge is Q1 for the first charge, and then M1 for the first mass, and then Q2 and M2 for the second object. And over on the right here, I'll start a list of givens. So what we've been given is that M1 is equal to M2 is equal to 2 grams. Grams is a non-SI unit, so we want to convert that to kilograms by dividing by 1,000. And then Q1 is equal to Q2 is equal to negative 50 nanocoulombs, we're told. And nano is not a prefix, a metric prefix that we've used a lot or in Physics 1, but it is a prefix that we'll see a lot in Physics 2. And just to refresh your memory, 1 nano of anything is equivalent to 10 to the minus 9 of that thing. So 1 nanocoulomb is equal to 1 times 10 to the minus 9 coulombs. And so therefore, using this conversion factor, we could write that Q1 is equal to Q2 is equal to negative 50 times 10 to the minus 9 coulombs. And that's the number that we'll need in our calculation. And then the last piece of information we're given in the problem description is that the two charged spheres are placed 2 centimeters apart. If you have a ruler, you might look to see how far is 2 centimeters. What I've drawn here is further apart than 2 centimeters. But it's always good to we're starting to get a physical intuition for how much charge, how much distance goes into creating an electrical force. So it's not bad to have a ruler nearby so you can look to see what 2 centimeters represents. So what we're given is that R, the separation distance, is 2 centimeters, which converted to meters is 0.020 meters. And then I'm just going to label the charges to make it clear to myself. These are both negative charges, so I'll put a negative sign inside of them so I remember that these are two like charges. So when we're calculating the force that each exerts on the other, charge 2 is exerting a force on charge 1, which is to the left. This would be the force of 2 on 1. It's the force of repulsion. And charge 1 is exerting a force on charge 2, which is to the right. Also a force of repulsion. These two forces are opposite in direction, but equivalent in magnitude. And to calculate, so F2 on 1, the magnitude, is equal to F1 on 2. And I'll call that force magnitude just F. And that force magnitude, which is what our target is, our target is to figure out the magnitude of this force F. And so to calculate that, we would use Coulomb's law. And F is going to be equal to K, the electrostatic constant, times the magnitude of charge 1 times the magnitude of charge 2 divided by the distance squared. And then all that's left to do is to plug in the numbers that we have in our list. So F is going to be equal to K as the electrostatic constant, 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. And the magnitude of the two charges, it's identical, so I'll just write it once here and square it. It's 50 times 10 to the minus 9 coulombs, and we're squaring it. And I've dropped the negative sign because we're looking for just the absolute value of those two charges when calculating the magnitude of the force. And then I want to divide by the distance squared. So that's 0.020 meters. And so if we run that through a calculator, what we find to two significant figures is 0.056 newtons. And so that would be the magnitude of the force exerted by one of the spheres on the other. And the directions, again, since these are two like charges, would be in opposite directions as a repulsive force. So they're exerting a force on each other to push each other away. Okay, so before giving you a lecture quiz question where you get to apply Coulomb's law, what I want to point out is just a couple things about Coulomb's law that are of interest, and it's always good to take a new equation and test it against our intuition. One of the things that Coulomb's law says is that the strength of the force exerted between the charges is going to be proportional to the product of the charges on the two objects. And I think this is consistent with our intuition in the sense that we know if we get more charge on an object. So for example, in the last lecture, I was doing a demonstration with a balloon and I rubbed it with fur. If I rub more vigorously, I'm going to transfer more charge to the balloon. Then we expect the force between that balloon and any other object to be stronger. So the first part of Coulomb's law just says that the strength of the force is proportional to the amount of excess charge that we've been able to apply to the object. And the second thing Coulomb's law says that we can test against our intuition is that the force strength is inversely proportional to the distance squared between the two objects. That is, the further apart the two objects are, the weaker the force. So if R goes up, the force strength goes down. And so if we separate the balloon from whatever we're having it exert a force on, then the force that object feels is not going to be as great as it would be if the charged balloon was closer. And this is something that you can experiment with in lab next week. You'll be working with charged pieces of tape. And I think you'll be able to see that the force strength depends on how close together those charged tapes are. So this is also, I think, consistent with our intuition and our experience. And even more precisely, what the inverse square nature of this law says is that if we have two objects, this is shown in the bottom right graph, if we have two objects that are separated by a distance r, then the force strength is F as shown here. But if we double the distance to 2r between the two charged objects, then the force doesn't go down by a factor of 2, it goes down by a factor of 4. And that's because the force depends on 1 over the distance squared, not 1 over the distance. And so then if we triple the distance, so we now have a distance between the two charges of 3r, then the force strength goes down by a factor of 9. So the electric force falls off very dramatically with distance. The further apart the objects are, the weaker the electric force is going to be. The other thing I want to point out about Coulomb's law is that it is an example of Newton's third law force, in that the force that one particle exerts on the other is equal and opposite to the force that the other particle exerts on the first. So in the example shown here, we've got two charges, Q1 and Q2. The force that charge 2 exerts on 1 is away along the axis connecting the two charges because they're like charges. And then the force that 1 exerts on 2 is shown as being in the opposite direction. But the magnitude of these two forces is the same, and that's indicated by the length of the two vectors being the same. So in equation form, we could write that F2 on 1 is equal to the negative of F1 on 2, where that negative sign accounts for the change in direction of one force relative to the other, as all third law pairs exhibit. But then in terms of their magnitudes, if we drop the vector notation, the magnitude of those forces is exactly the same. So I'll give you a lecture quiz question at this point to think about, and then I'll stop here, and then I'll come back and we'll look at another example of an application of Coulomb's law.